Welcome to our last class, everyone. Let's get started. Course announcements. There will be office hours at the normal time, 10 a.m. Montreal time, tomorrow, Friday. Are there any questions? Well, we always have access to videos and slides, or will my courses close them at the end of the term? I don't know if my courses will close them at the end of the term. However, the slides are available publicly on my website, and the videos are available publicly on YouTube with any video of participants. I tried to remove that, so it should be confidential, but on YouTube publicly. Of course, people's comments in the chat are also not public. Any more questions? Any plans on doing a follow-up class? I am not planning on doing a follow-up class to this, but I will be teaching other classes. So there will be more time for general questions, hopefully at the end of class, and I will stick around for a while after that. Let's get started with today. So today we have a busy schedule. We're going to be starting out with unsolved problems in math and going on to paradoxes and then going on to mathematical art. Very important things. Let's start out with some unsolved problems. There are a lot of unsolved problems in math and in mathematical computer science and theory. There are obviously way too many to talk about, and obviously any kind of research is solving something new. But here are some famous cool problems that it feels really strange that we haven't already solved. And it just sort of makes me happy to know that there is still something so exciting and something so easy to understand, where it's so easy to understand the question, but really hard to understand the answer. But yeah, there's so much we don't know. Let's start out with Goldbach's conjecture. So this is very easy to state. Every even integer greater than 2 is the sum of 2 primes. So for example, 100 is equal to 89 plus 11. That is the conjecture. It was conjectured in 1742. We still have no idea how to solve it. It's been checked up to 10 to the power of 18. Here are some of the first examples. So 4 is 2 plus 2, 6 is 3 plus 3, 8 is 5 plus 3, 10 is 5 plus 5, 5 plus 7, 7 plus 7, and so on. As you get lower down, you start getting many integers that have many different ways to write them. Like 22 can be written as 11 plus 11, also as 17 plus 5, and also as 19 plus 3. But even just showing that there is a way to write it. Just at least one way to write it. That is so hard. In general, you will find a lot of math conjectures, which are number theory conjectures about primes. We really don't understand the prime numbers. There are a lot of things that we do know, but basically we know things about the primes sort of all together and like the distribution of primes. roughly how many primes there are between two numbers and so on, but we don't know exactly what the primes are. So something specific, like there is a prime here and there is a prime here and they sum together to equal 100, that's something we don't know. Are there questions, thoughts? Please, this is very, very open to questions and discussion. Do you have to check numbers brute force to verify they are the sum of two primes, or is there a simpler way? That is a really good question. I don't know. I don't know if you just have to check all the possible sums. My guess is that it actually doesn't take that long, because I would guess that in many of these cases, there are lots of ways to write a number as a sum of two primes. Now, I also imagine there are probably heuristics where you can work out that you should be trying these things first, because there are numbers that are more likely to be prime for various reasons. If you want, you can look up the term probably prime, which actually is a real mathematical term. It refers to numbers that are more likely to be prime. Are there approximation algorithms? I don't know what it would mean to be an approximation algorithm for this. You mean like given that it's supposed to be true all the time, or approximation algorithms for whether something is prime? Yes, there may be. I'm not sure. But simply finding primes is not the conjecture. It is that there is always a way to write something as the sum of two primes. Let's go on to our second unsolved problem, the Collatz conjecture. So this is a game, sort of a game that you play with yourself. Take a positive integer, and if it's odd, you multiply it by 3 and add 1. If it's even, you divide it by 2, because you can. If you keep on doing this, you reach 1, is the conjecture. For example, if you start at 9, 9 is odd, so you multiply it by 3 and add 1. 28, so that's 9 times 3 is 27, so add 1, 28. That's even, so we can divide it by 2. This is even, so we can divide it by 2 again. Great, we're getting somewhere. 7. Oh, shoot, that's odd. Remember, we're trying to get to 1. So there is no choice here. We don't get to choose which one we do. We just, it's completely deterministic. At 7, since it's odd, we multiply by 3 and add 1, so 22. Then we get to divide by 2. We're sort of happy when we divide by 2 because it's going down. But then this reaches 11. 11, multiply by 3, add 1, get 34. Divide by 2, 17, multiply by 3, add 1, 52, 26, 13, 40, 20, 10, 5, 16, 8, 4. Yes, we're going to do it. We're going to do it. So that was how long it took to get from 9 all the way to 1. It took us going all the way up to 52. So it wasn't like it was going down all the time. It went up a long way, and then finally it came back down and hit 1. So the conjecture is eventually you reach 1, no matter where you start out. The conjecture was posed in 1937. Paul Erdős, who is one of the famous people in math, said, math may not be ready for such problems. It's so far beyond what we have an understanding of. We just don't know how to go about proving this. And there's similar things that people have said, with just within the last few years. It's been tested up to 2 to the 68. It's about 300 quintillion. So it does work for all of those numbers, but maybe past that, there is a number that it doesn't work for. Is there a reduction to the halting problem? This is not, it's not that this is unprovable. It's that it's not, I'd be interested in seeing seeing what you're saying there, because there are problems which we know in math cannot be decided. The halting problem is something which we know can't be done. So there's a comment saying there's a classic reduction to the halting problem. I'm not familiar with that, and I'm somewhat skeptical, because if this were equivalent to the halting problem, then the halting problem could, we know that the halting problem just simply cannot be solved. Some detail about what aspects are beyond or within our current understanding. I have no idea. This is not something I've worked on. I just think it's really cool. I think it's really cool. This is a problem which, you could almost get given at a party and be like, oh, why is that true? And then start thinking about it. And then, 50 years later, still be thinking about it. More questions, comments? So can't we just say this works up to 2 to the 68 and just be happy with it? If it must be used in a real life scenario, doesn't it cover most cases? Yeah, it's not going to be used in a real life scenario. This is not something that is practical. This is just for the joy of the thing. Because we want to understand why this is true. But also because sometimes the proof itself will give us insights into some other situation. So, sometimes by coming up with the math to prove something which is useless, we accidentally come up with the math to prove something that is useful. And yes, I would be tempted to try monovariance proof too. I'm looking at it and I know that people have been wrestling with it for the past 100 years, and I'm still tempted to try a monovariance proof. I still feel like, oh, maybe there's just a way, but no. There may very well be a way, but it is probably not a simple way. But then sometimes, I guess I don't have an example of this, sometimes there is a problem that people haven't solved for decades, and there really is a fairly simple solution. So. Here's something useful, matrix multiplication. So we saw in class that multiplying m by n and n by p matrices can be done in time theta of m and p. You can do it. If m equals n equals p, then that's theta of n cubed. But that's not necessarily the fastest way that you could do the multiplication. So there is a way to multiply it in theta of n cubed, but there may be a faster algorithm. This was just a sort of naive algorithm. So here's a question. Why, if you're multiplying square matrices that are n by n, why does the fastest time have to be omega of n squared? So at least n squared. For just multiplying two matrices, just two matrices, an n by n and an n by n. If it's just general matrices. Yeah, so you need to at least look at all the n squared entries in one of the matrices, and also there are n squared entries in the other matrix too. So it's just to look at the matrices, it's going to take at least n squared. So somewhere between n squared and n cubed. Or alternatively, to write down the answer, it'll take n squared. Somewhere between n squared and n cubed. Okay. So what's the answer? Anyone know? What's the most efficient time for multiplying two n by n matrices? This is dense matrices. They're not assuming the matrix is sparse. And somewhere between n squared and n cubed. You're not going to be able to do better than n cubed, than n squared. And we know that we can do it in n cubed. So currently the best known algorithm is O of n to the 2.3728596 approximately. That was created a few years ago. It's pretty recent. It is not known what the best exponent is. There are many papers which just assume that they write a constant for this, just n to the some constant, omega, where omega is just the best matrix multiplication exponent. We don't know what the best number is here. Now, in practice, you might not want to use this algorithm because the constant might be very large. The number, I don't know where the number comes from. I don't know what the number comes from. There are ways to get simpler algorithms, which are less than n cubed, where you can actually like look some of those up, like Strassen's algorithm, and you can there are algorithms that are quite understandable. I think this algorithm will probably be more complicated. And yes, as people are saying in the chat, if you have sparse matrices with only a few entries being non-zero, that is absolutely much faster. You can do it faster than n squared. This is for general matrices. Now, there's a comment on the previous slide saying that if you had an answer to the halting problem, then you could determine this, because if this halts, if this finishes, then you can turn it into a halting problem. Yes, so if you could solve the halting problem, then maybe you could solve this, but we know that we can't solve the halting problem. It doesn't go the other way around. It's not if you could solve this, then you could solve the halting problem. So that's, yeah, sorry, then what you said before was totally fine. It was just that if we know that we can't solve the halting problem, so that doesn't actually help us. But yes, agreed. No, sorry, that was me misunderstanding, and you wrote everything correctly. In Collatz, does it eventually mean non-infinite time? Yes, non-infinite time. For every number, there is a certain amount of time, a finite time at which it hits 1. Graph isomorphism. Two graphs are said to be isomorphic if we can reorder the vertices so that they line up. And all the edges line up. So for example, here is one graph. You can see it's a bipartite graph, these vertices labeled. And here is another graph, and these vertices labeled differently. This is an isomorphism where you can identify these two vertices, these two according to the colors here. And you can check that it matches up all the edges. So the edges are blue, red, blue, green, blue, orange from the blue vertex. And here, blue, green, blue, red, blue, orange, and so on. Let's define a decision problem. Isomorphism of GH. The problem of working out whether two graphs, G and H, are isomorphic. We do not know what this problem is. It may be in P, it may be NP complete, or it might be neither. NP intermediate. It is not known which it is. I'll let you think about this. Now, there are various obvious ways that you could say no if you were given two graphs and you were told, are they isomorphic? You might be able to say no, for example, if they have different numbers of vertices or different numbers of edges, or the degree, if you made a vector of all the degrees, maybe those weren't the same vector. Maybe the degree of one vertex is in one graph, the maximum degree is, it has 100 edges, and the other one, it has 101 edges. So then you know that you can't match those two graphs up. But in general, it is an NP. It's just not necessarily NP complete. You are correct. It is definitely an NP. The goal is not to find the isomorphism, it's to determine whether the graphs whether there is an isomorphism. So for example, if I took out this edge, there wouldn't be an isomorphism anymore. There wouldn't be a way to shuffle around the vertices in one graph to get the other graph. Questions, thoughts, conundrums? And let's end with one that actually has been solved. So if we have to divide a flat surface into equal areas, a hexagonal honeycomb is the method to do it with the least total perimeter. If you have a certain amount of, wax to build your dividers between your little areas, and you have this really big area that you need to divide into equal areas, then hexagonal honeycomb is the best way to do it. This was conjectured in 36 BCE. And obviously bees have been doing it for quite a while. It was proven in 1999. So sometimes one of these conjectures that's been around for millennia does actually get proven. There are a bunch of related problems that are not known. I actually don't know how the proof went. It was by somebody called Hales. How often are such theorems proven? I mean, there are a lot of unsolved problems. There are more unsolved problems than solved problems. Maybe not like named unsolved problems, but there's just so many. There's just a lot that we don't know here. Don't the bees actually make circles and then the wax forms into the hexagons? So I don't know how the bees actually do it, but there is definitely sort of self-assorting into hexagons. And one of the cool things you can do is you can look at this with bubbles. You can see that angles between bubbles like work out to form hexagons in certain contexts. So some of this sort of happens naturally, but yeah, just because it's the way that something happens naturally doesn't mean it's necessarily the most efficient thing. Okay. Now let's look at some surprising math or seeming paradoxes. Let's prove that all horses are the same color. So we're going to use induction. I'm going to show that any group of n horses is the same color. I'm going to do induction on n. Before we do this, there's an unrelated question. Once you have a proof, how do you make sure that it's correct? I heard that the proof of Fermat's last theorem is crazy long. How do peer reviewers make sure they interpret a proof correctly? It is super, super hard. There are a lot of mistakes that happen. Now, most of the time, basically, if a paper is read enough, then somebody will find an error in it if it exists, probably. So the errors that occur in papers generally are either before the paper has been really read widely, or before, or if it's something that was never really like read very much. But sometimes it does get through peer review. Sometimes it does get through peer review. I don't think that the proof in the case of Fermat's last theorem was already peer reviewed, but I'm not sure. I don't think it was like that. It was peer reviewed. So Fermat's last theorem was solved a few decades ago. It was the first time the mathematician declared it to be solved. It was not solved, and the proof was actually wrong. And that mathematician went back and was like trying to fix the proof, and then a year later, I think, came back and fixed it. And so it was actually solved then. But that's not a feeling that I want to have, going out and saying, you know, I've solved this fantastic problem and having somebody point out, nope, not true. There's this problem in it. But then fortunately there was a way to fix the proof. But yeah, so there isn't a good answer here. I mean, there are ways of formally checking things, but typically people don't go through formally putting something into a computer to check that. And also it's really hard for complicated proofs. Our automated proof checkers are, I think, not, I wouldn't imagine that they would be good enough to check something like the proof of Fermat's last theorem, but maybe. Okay, let's go back to proving that all horses in the world are the same color. So again, we're using induction to show that any group of n horses is the same color. Base case, just one horse. Clearly one horse is the same color as itself. If you have just one group of one horses, then everything's the same color. Okay. Now let's have an inductive hypothesis. Let's suppose that any group of n horses is the same color, and we're going to show this for n plus 1 horses. So we have a group S, which contains n plus 1 horses. We need to show that all of them are the same color. So let's consider the set S1, where we take out the first horse from S, and the set S2, where we take out the second horse from S. And so remember, S is this group of n plus 1 horses. And we've taken out one horse to get the first group, and then we put that horse back in and take out another horse to get the second group. So both S1 and S2 contain n horses, because each of those was what we got from S by taking out a different one of the horses. So by induction, we know that all the horses in each one of S1 and S2 are the same color. So like in S1, within S1 just by itself, all the horses are the same color. And within S2 by itself, all the horses are the same color. Okay. But these sets, I mean, you only have this one difference between them. So S1 was by taking out the first horse, and S2 was by taking out the second horse. And so in all the other horses, S1 and S2 are the same. They just differ by this one horse. And so since they overlap, the colors have to be the same. So we had all the horses being the same color in S1 and all the horses being the same color in S2. And so the same color in S1 had to be the same color in S2. So all the horses overall are the same color. We're done with the induction. Why horses? Why not zebras? I mean, I think zebras are already 2 colors. What's wrong with this argument? Why do we suppose that any group of n horses is the same color? It was an inductive hypothesis. We said, okay, base case of n equals 1 works. Now let's suppose that it works for n. Let's go to n plus 1. What's wrong with the argument? The base case should be n equals 2. Why should the base case be n equals 2? I mean, base case of n equals 1 is perfectly fine. What was wrong here? We could, if, induction, we can do base case of anything, as long as the inductive step works. Saying that by induction, we know all the horses in each one are the same color. No, that's perfectly fine. S1 and S2 contain n horses. We know that n horses, by our inductive hypothesis, had, suppose that this were 10 horses, we would assume that every 9 horses have the same color. So each of these has 9 horses. And so by our inductive hypothesis, we know they have the same color. And we assume we've already proven it for 9 because it was induction. Haven't you assumed that every horse in the world is the same color? No, we just assumed that in a group of n horses, everything was the same color. Ah, so this is the one phrase that's wrong. Every other part of the proof is correct. Every other part of the proof is correct, since they overlap. Why do they overlap? Well, we said that they differed in just one horse, so they had to overlap. But what if n equals 2? Sorry, what if n equals 1 here? We're going from n equals 1 to n plus 1 equals 2. In this case, these contain, S1 contains 1 horse, S2 contains 1 horse. And they don't overlap. So the idea is that if we could prove the answer for 2 horses, then we could prove it for 3 horses and 4 horses and 5 horses and so on. But we can't actually go from 1 horse to 2 horses because S1 and S2 don't overlap in this case. I'll let you stare at that. It was a classic example of a proof that seems good but is actually not good, which is fortunate because if we could prove nonsensical things, then there would be something, then we wouldn't want to use math. There's a question about why you can assume all horses are the same, n horses are the same color. This was an inductive hypothesis. For some fixed n, sorry, I guess I should have said any group of n equals k, like some specific, suppose, so in induction, we say, suppose that we know it's true for one n, then we prove it for the next n, for n plus 1. So here we're just saying, let's suppose it's true for n, now we're going to prove it's true for n plus 1. Can that be false in the world, though? Of course, this is not a real world proof. This is just supposing we are seeing if, without any knowledge of the world, we can prove that any n horses are the same color for any n. This is not a real world based proof. This is a proof based on pure logic. And we're trying to see if we get a contradiction using pure logic of something that is clearly true in the world, which is that there are different colors for horses. So the goal here is to see if logic fails us. And fortunately, it does not, because the reason why our induction doesn't work is because we assumed that we could prove it for 2 horses, where in actuality, we cannot go from the case of n equals 1 to the case of n equals 2. Did we prove it or not? We did not, fortunately. If we did prove it, then there would be a contradiction in math. This would work if this is the one problem in the proof. This breaks everything. We assume that we can do our induction. We can say, assume that it works for some n. Let's see if we can prove it for n plus 1. But we can't. When we took our sets S2 and S1, we assumed that they overlapped, and they don't overlap necessarily. in the comments, thank you for giving us lots of facts about honeybees. Let's move on to another paradox. So this is something that's actually called a paradox. I'll come back to the other question at the end. So two new pet medicines for pets, A and B, are tried on some cats and some dogs. These are the rates at which the medicines are successful. There are 200 trials in cats, out of which 120 are successful, 60%. In dogs, there are 50 trials in medicine A, out of which 5 are successful, so 10%. For dogs, there is a 40 out of 200 success rate for medicine B, so 20%. And cats, 80 out of 100, 80%. And don't worry, it's not that the dogs are suffering. This is a medicine to make pets less grumpy, and maybe it's because cats are just always grumpy. So medicine B performs better than A in cats, and it also performs better than A in dogs. You can see that here in cats, B is better than A, and B is better than A in dogs too. Great. So clearly we want to try medicine B. Let's add another row to the table with totals. Overall, medicine A, there were 120 plus 5 successes out of 200 plus 50 trials. So 50% of the time it was successful overall. There were 80 plus 40 successes of B out of 100 plus 200, or 300 total trials. So it's a 40% success rate. Wait, what? Medicine A is now better than medicine B overall. Even though for cats it was better, and for dogs, sorry, cats B was better, and for dogs B was better. Suddenly now medicine A is better. What happened? Is this along the lines of can't compare apples to oranges? Not really. These are all perfectly correct statistics. There's imbalance between the number of trials. Yeah, so the reason this happened was because for A, there were different numbers. In all of these cases, there are different numbers of trials for A and B. The test happened for A mostly in cats. And cats, overall, both medicines did well. Whereas for dogs, for medicine B, sorry, most of the tests happened in dogs, where neither medicine performs well. So if you're looking overall, well, medicine A is going to perform better because more of the trials happened in the patients which responded to medicine well. Whereas for B, most of the trials happened in patients which didn't respond to either medicine very well. This literally happens in medicine. Like, you can't always control the number of patients in each one of these sections of the diagram, in each one of these cells. There are situations where legitimately Simpson's paradox occurs. And it's super important to break out the confounding variables in your studies so that you don't end up with this. Because if you didn't break it down by cats and dogs, you would think that A was better. And the conclusion, which you probably should draw here, is that B is better because for cats it's better and for dogs it's better. And if you were doing it if you were sampling equally, you would probably get that B is better. This is not a, it's not a paradox, as in this is not a contradiction. It is something that seems really strange. Or I know when I saw it, I thought it was really strange. And sometimes you're just given these percents. Like you don't know how many samples there were in each group. So sometimes you just say, you know, for this group it was better, and for this group it was better. And sometimes in other cases you say, well, overall it was worse. Can't we weight the percentages by the number of trials? Yes, you can weight things by the number of trials. You can do weighted averages. But this is just literally an average. So it's like, it is all three of these rows are correct ways of doing the statistics. It's just there are several different ways to do it. And these two are better than this one because this one is not accounting for the confounding variables, but it is correct. It's not like mathematically wrong. It's just misleading. Here's another example. Let's see another example. So this is an imaginary plot. It's not a plot that is actually drawn from real data, but it's a plot that you might imagine having of sleep versus life expectancy, with each of these dots being a particular individual. So there are two ways that you could imagine analyzing this. You could first imagine analyzing it by doing a linear fit for all the data, a black dashed line. Ignore the colors for the moment. There are these points up here, and there are these points down here, so a good linear fit is basically like this. So we get that more sleep means lower life expectancy. So if that were the only way you analyzed your data, by doing just a single linear fit, then you would conclude more sleep means lower life expectancy. But if you actually look at the data, sort of an intuitive look at this means, oh, well, there's a trend up here and there's a trend up here. If you can break it into two groups, the red group and the blue group, well, it turns out the red group is dogs and the blue group is people or humans. So dogs sleep more than humans, and they have a lower life expectancy. But for both groups, for each group individually, more sleep is good. If you're a dog, then more sleep is good. If you are a human, more sleep is also good. It's just dogs happen to be sleeping more overall than people, and they also tend to have lower life expectancies. So for each group individually, there's a trend up. But if you combine them, there's a trend down. This is why it's important to break out confounding variables. And this is basically the same effect between the two different examples. Questions? Why is it called a paradox? It's more like looking at data from the wrong perspective. It's true. Like, I personally found it surprising that you could have these two things be greater and then this be greater. But yes, it is looking at data from the wrong perspective. Very few things are actually internally contradictory. And math is not actually internally contradictory. Here's another thing that is surprising. I mean, it's not a paradox in that it doesn't lead to a contradiction. Suppose we have 3 dice. A has sides, they're both all of these are 6-sided dice. A has sides 2, 2, 4, 4, and 9, 9. B has these sides, C has these sides. Let's calculate the probability that A rolls a higher number than B. What is the probability that A rolls a higher number than B? Well, let's go through the cases. There are 3 possible settings of A, and there are 3 possible settings of B. Let's look at which combinations the settings of A and which combinations of the settings of B give us that A is greater than B. Well, we could have 2 and 1, 4 and 1, 9 and 1, or 9 and 6, or 9 and 8. So that's 5 different possibilities, and there are 3 times 3 different choices overall. So it's 5/9 probability that A is greater than B. Similarly, B is greater than C if we have any of these situations: 6 and 3, 6 and 5, 8 and 3, 8 and 5, or 8 and 7. Again, there are 5 possibilities out of a total of 9 that would give us B being greater than C. And likewise, you can find that there's a 5/9 probability that C is greater than A. Here's a way to graph it. The probability that C is greater than A, or in 5 of the 9 possibilities, C is greater than A. In 5 of the 9 possibilities, A is greater than B. In 5 of the 9 possibilities, B is greater than C. So if you rolled all of them together, it is more likely than not that C is greater than A. It is more likely than not that A is greater than B. And it is more likely than not that B is greater than C. There is no contradiction here. It is just something that is really confusing, at least to me. Surprising that you can have it be that it be more likely than not that each one of them beats the next one. This is a question. Is there a 6/9 probability that No, I don't think so. 3, 2, 5, 4, 3, 2, 5, 2, 7, 2, 5, 4, 7, 4. Oh, yes. Yeah. So in some sense, there isn't a, the pairwise interactions between the dice are sort of like, it's like a rock, paper, scissors thing. Again, this isn't internally contradictory. It just gives you something that's weird and surprising. Are there questions about this? There's a question about the previous, a couple of questions about Simpson's paradox. Is there a quantitative method to evaluate if you're faced with Simpson's paradox? So that gets into causality. It's complicated. I'm happy to talk about that more. It's a really good question, but it's basically an entire field. Is there a method for finding confounders by assigning random subgroups, fitting them, and see how many contradictions you get? There are a lot of possible subgroups that you could get. What if you roll all 3 at the same time? Well, we're not looking at the probability that one of them is the greatest. We were only looking at the probability that individual pairs of them were greater than each other. So yes, you can imagine rolling all 3 at the same time, and simultaneously it is more likely that A is greater than B, is more likely than not that B is greater than C, and is more likely than not that C is greater than A. Which would seem on the face of it maybe to be internally contradictory, but it is not. We're going to close by going through very quickly some mathematical art. Now, there is a lot of mathematical art out there. I just wanted to give you a little sampling in conclusion of the course for some of the ways that you can visualize really cool things. I realize we haven't really talked about geometry, and a lot of art is geometric, but just to get a sense for some of the ways that there are mathematical constructs that can be used to make really beautiful things, like physically beautiful things. So this is based upon a dodecahedron. You can sort of think of it a bit like a soccer ball. I don't know all of the geometry involved here, but it is perfectly symmetric with dodecahedral symmetry, I guess, except for the pedestal. I'll put up these slides afterwards if you want to look at things more. This is a design made out of string. There is a very simple rule about, I actually have one of these in my house that I made. You have a very simple rule for working out which these equally spaced holes you connect up to other holes. And when you connect up holes in this particular way, you get this beautiful shape, which is called a cardioid. There's a nice equation in polar coordinates for this shape. Cardioid means heart, because it sort of looks like a heart if you tilt it. This is a one-sheet hyperboloid. It is what happens if you take a line and you rotate it about another line that it doesn't intersect in three-dimensional space. So here's a line, you take this line, you rotate it around. That's what these lines are. They are rotations of the same line about a central axis. And there are other lines going the other way, which are also rotations of each other around the same axis. So there are two sets of lines which all cross, or all rotate. It's hard to visualize unless you're physically looking at it. And this is lit, so there's this beautiful shadow going on. Tessellations, made famous in particular by Escher. These are tiles that repeat in a beautiful pattern that can go on forever. Tessellation means that these are like shapes which are repeating, and you can just keep on sort of stacking them in this repeating pattern. There are a lot of really complicated, beautiful ones by Escher and by other people as well. And then finally, to close, the Penrose tiling, which is a tiling that can go on to infinity like a tessellation, but it is not repeating. It will never repeat for all of infinity. There are just these two shapes, the blue diamonds and the green diamonds. They're repeated infinitely many times, going off to infinity. And you can tile, your infinitely large kitchen floor. You can tile it completely with Penrose tiles, but it will never repeat. I am happy to talk about fractals offline, and I'm happy to stick around for some more questions. But that is the end of today, and that is the end of the course. There will be office hours on Friday at the normal time, and I will be available on Slack. I'm also very happy to answer more questions even after the Slack is active by email. Feel free to reach out. It's been wonderful having you all in the course. Thank you so much for being a part of this. I am just excited to see what you do with math and computer science individually and together moving forward. Thank you.